And so we are going to prove that if n is an integer and the square root of n is not an integer, then the square root of n is irrational, and we do this by descent. And we recall that by the well-ordering principle, every non-empty set of positive integers contains a least element. And if n has a non-integral square root, that will be between two numbers, p squared and p plus 1 squared, which do have integral square roots, and we can take the square root of each side of that inequality. And so taking the square root of each side of that inequality, we can see that p is less than the square root of n, which is less than p plus 1, and that gives us the most important result, that the square root of n minus p must be less than 1. Now, suppose that this square root is actually rational, represented by some number a over some number b, where big A and big B do not necessarily represent the square root of n in its lowest terms. So there'll be an infinitude of fractions a upon b, which, if root n is rational, will express this. And we are going now to assume that this one here, this representation here, small a over small b, is the root expressed in its lowest terms, where divisor of those two numbers equals 1. And so lowercase b must be the smallest integer, such that when you multiply it by root n, you get another integer. So if we call that root n minus p is smaller than 1, then b times root n minus p will be a member of the integers, and b times root n minus p will be smaller than b. But this b, root n minus p, is smaller than b, and when you multiply it by root n, you are going to get another integer, as we shall show. So that if I take b root n minus p, which is less than b, and I multiply it, which I've done inside the brackets there, by root n, I get b times n, which must be an integer, because both b and n are integers, minus p, b, root n. But b root n is itself an integer. Therefore, pb root n is another integer. So what we have there is one integer minus another integer, which gives us an integer. But remember, b was supposed to be the smallest integer, such that when you multiplied it by root n, you would get an integer. And then we took b times root n minus p, which was less than b. We multiplied that by root n, and we once again got an integer. So there can be no smallest integer, such that when you multiply it by root n, you get another integer, and yet by the well-ordering principle, such an integer must exist. And so by infinite descent, the non-integral square root of any integer is itself an irrational number.